What if you could replace worn-out body parts as you aged? Someone took your breath away? Breathe easier now. Got your heart broken? No problem. Liver not what it used to be? Here's a new one. Weak in the knees? How about a new joint? This concept of substituting organs or joints with replacements is not new to science fiction. There are many characters that have mechanical replacements for broken or worn-out body parts. Sound far-fetched? Not to the million or more people each year in the United States that receive artificial joint replacements made out of plastic and metal. While the replacement joints ease pain, they do not impart superpowers. Instead, they are expensive and not very durable. It turns out that nothing glides better or is as durable as a natural joint. That is to say, synovial joints are the most frictionless surface known to science, slicker than even ice on ice. So instead of becoming part machine, what if you could use a machine to make new parts? This idea of a biological cyborg is just what scientists are working on now. So, where do you start in order to print yourself a new knee? With the cells that make articular cartilage, chondroblasts. These cells produce the extracellular matrix of cartilage. However, once the matrix is created, the chondroblasts are entrapped within the matrix. Although this may seem problematic, they soon assume a new role signified by their new name, chondrocytes. These mature chondrocytes no longer produce cartilage, but instead work to maintain its health and produce enzymes for cartilage metabolism. However, they are not an optimal source for making a new knee. Instead, scientists turn to stem cells as a source of chondroblasts. Stem cells are undifferentiated cells that are capable of giving rise to an infinite number of cells. From these cells, other kinds of specific cells can be derived in a process called differentiation. At UCSF, scientists discovered an exciting way to obtain stem cells. It turns out there are isolated genes that can induce a differentiated cell, in this case, skin cells, to de-differentiate back into stem cells. The result are cells called induced pluripotent stem cells. They get the name induced because they have to be manipulated to de-differentiate. And they get the name pluripotent because they have the capability of becoming all different cell types. Here's how it's done. Genes are inserted into a virus vector. Inserting the genes into a virus enables the genes to be inserted into the cell by infection from the virus. Unlike the common cold, this infection proves useful. Once the genes are present in the cell's own machinery de-differentiates back into a pluripotent stem cell, capable of becoming different types of cells, including chondroblasts. This has proven to be effective with skin cells. However, there are some drawbacks. Because of iPSC's versatility, they are difficult to control and may differentiate into an unwanted cell type. As a solution to this, scientists have recently discovered a supply of stem cells from an unlikely source, and it's a source many people would be happy to donate. Adipocytes, aka fat cells. Adipose cells are a rich source for obtaining stem cells. Once these cells are harvested, by combining platelet-derived growth factor and the drug azacitidine, the cells are rendered amnestic, or in other words, they forget their differentiated functions. These cells are called induced multipotent stem cells. They are called multipotent, not pluripotent, because they can only differentiate into a limited number of cell types, one of those being chondroblasts. Now scientists can use these cells and differentiate them into chondroblasts. If these cells are left in the in vitro-like environment of a petri dish, they can begin to produce the extracellular matrix of cartilage. But it turns out it is not enough to make cartilage in a petri dish because it does not have the same structure as natural cartilage. Cartilage found in human joints has a complex macrostructure consisting of 5 zones based on the orientation of collagen, the most important protein in cartilage. The superficial layer begins with the tangential orientation of the collagen and changes from oblique to vertical until it finally transitions into bone. These zones provide resistance to compression and anchor the cartilage to bone. This has proven to be very important, as without these 5 zones, cartilage does not have the same compressive strength and durability. Thus, the second component of cartilage, the extracellular matrix, benefits from scaffolds. In this case, scaffolds are used as a framework or outline for the cartilage. Think of them as a scaffold for a building. When scaffolds are used in buildings, they are only temporary and are replaced by, for example, bricks. Here, scaffolds are seeded with chondroblasts and made out of biomaterials, so over time they are replaced by the collagen and proteoglycans produced by chondroblasts. In order to mimic natural cartilage, scaffolds must be durable, have the ability to integrate with native cartilage, and have the same mechanical properties as natural cartilage. Researchers at Columbia University have developed a scaffold that exhibits these qualities and replicates the zonal structure of cartilage with osteochondral scaffolds. Osteo means bone, and chondral means cartilage. So the graft has the cartilage scaffold and the bone scaffold connected already. This makes it much easier for the scaffold to adhere to the knee, as bone attaches more reliably to bone than cartilage does. These scaffolds would be comprised of an agarose layer and a devitalized bone layer, and they can manufacture these using 3D printers. Other researchers recognized that the knee is a moving environment and discovered that cartilage needs a dynamic environment. They developed a biodynamic stimulator in which developing cartilage experiences a dynamic environment similar to a human joint. It is called a hydrostatic pressure bioreactor. So what does the future look like? Adipocytes may be used to make iPSCs, and a scaffold could be printed with a 3D printer. The scaffold could then be seeded with cells and then developed in a biodynamic stimulator. Finally, the scaffold could be surgically placed in the knee.
Reality truly is stranger than fiction, or in this case, science fiction. In the future, knees may no longer be replaced with a metal knees resembling a cyborg. Instead, it may be even more fantastic. Our biological cyborg may have new cartilage made of fat. Thanks for watching.